What lies above and below our galaxy? This question stretches beyond simple curiosity. It is an invitation to peer into the unseen architecture of the universe. Our galaxy, the Milky Way, is not an island adrift in perfect isolation, but a vast system layered with hidden structures, invisible matter, and cosmic flows that extend far beyond the glowing arms we see in the night sky. To look above and below is to trace the outlines of these mysterious realms, uncovering forces and formations that not only define our galactic home, but also link it to the larger web of the cosmos. The answer is both familiar and alien, a reminder that even in regions we often think of as empty, the universe is alive with unseen order. The mystery of what lies above and below our galaxy begins with the recognition of its central framework, the galactic plane. The Milky Way is not a random scattering of stars floating in all directions, but instead a structured, flattened disk that defines our perspective of the night sky. This disk is our galaxy's foundation, and when we speak of above or below, we are referring to positions relative to this massive thin plane. It is here, within this concentrated layer of matter, that most of the luminous life of the Milky Way unfolds. The galactic plane is the heart of the galaxy's visible brilliance, and yet it is also the boundary line from which everything beyond, halos, clusters, voids, and cosmic flows, must be measured. The disk itself is remarkably thin compared to its enormous breadth. Its diameter stretches over 100,000 light-years, yet its thickness in the thin disk is only around 1,000 light-years. To put this in perspective, if the galaxy were scaled down to the size of a dinner plate, the thickness would be no greater than that of a sheet of paper. This contrast in proportions is why, when we gaze across the sky on a clear night, the Milky Way appears as a dense, hazy band arcing from horizon to horizon. That glowing ribbon is not some distant structure. It is the collective light of billions of stars packed into the galactic plane, so numerous and so tightly aligned from our vantage point that their glow merges into a single radiant stream. This sight, visible to the naked eye, is our direct experience of living inside the galactic plane. The stars that dominate this thin disk are relatively young on cosmic timescales. Here, star-forming regions such as nebulae, vast clouds of dust and gas, light up as stellar nurseries creating clusters of newborn stars. Spiral arms, the defining aesthetic feature of the Milky Way, are themselves manifestations of density waves traveling through the disk, sweeping up material and stimulating waves of star formation. Everything we typically imagine when thinking of a galaxy, the glowing stars, the vibrant nebulae, the swirling arms, resides within this thin, crowded plane. Even our Sun, with its orbit circling the galactic center once every 225 to 250 million years, is a part of this vast, rotating stellar disk. We are not above it or outside it. We are embedded within it, surrounded on all sides by its dazzling architecture. But while the galactic plane is the most striking and visible feature, its crowded beauty masks its limitations. When astronomers peer outward from within this plane, their view is obstructed by the dense fields of dust and gas that fill its lanes. This obscuration makes the central bulge of the galaxy, where the supermassive black hole Sagittarius A resides, notoriously difficult to observe in visible light. It is only by using infrared and radio telescopes that scientists can penetrate this curtain and glimpse the energetic heart at the core. In this sense, the galactic plane is both a window and a wall, illuminating the richness of galactic life while simultaneously concealing deeper truths that lie hidden behind veils of interstellar matter. Another feature of the galactic plane is its remarkable thinness compared to the populations of stars that exist slightly above and below it. The thin disk, which dominates, is home to stars like our Sun, relatively young, metal-rich, and actively part of the galaxy's ongoing cycle of creation and destruction. Yet, even within this plane, there are structural differences. A thicker disk population also exists, stretching a few thousand light-years above and below, populated by older stars with different chemical signatures. This difference foreshadows the layers beyond. But even within the galactic plane itself, we can trace the story of the Milky Way's evolution, seeing how new stars rise from gas clouds while older ones drift farther from the bustling mid-plane of activity. The galactic plane is also a crucial reference point in mapping the heavens. Astronomers use it to establish galactic coordinates, defining the orientation of our galaxy in space. When we say something lies above or below, it is always relative to this midplane. Just as Earth's equator divides north and south, the galactic plane divides the Milky Way into a kind of celestial hemisphere, with all larger-scale structures, halos, clusters, and cosmic flows, extending outward from it. Without this plane as a marker, the very concepts of above and below in cosmic terms would lose their meaning. What makes the galactic plane especially intriguing is that it is not static. Over billions of years, the disk has warped and rippled, influenced by gravitational interactions with nearby dwarf galaxies and satellite systems. Recent surveys have revealed that the Milky Way's disk is not perfectly flat, but exhibits a pronounced warp, bending upward on one side and downward on the other. This warp may have been caused by the pull of the Sagittarius dwarf galaxy or other satellite galaxies as they pass near or through the Milky Way. Such distortions remind us that the galactic plane is not simply a fixed foundation, but a dynamic, evolving structure that reflects the constant tug-of-war of gravity shaping its form. Moving beyond the disk of the Milky Way reveals a transformation in the structure of our galaxy that is both subtle and profound. The thin galactic plane, crowded with stars, nebula, and gas clouds, is only a thin slice of the Milky Way's true extent. As one rises above or falls below this plane, the scenery changes dramatically. The stars begin to thin out, no longer densely packed together in clusters of radiant brilliance, but instead appearing more sparse and isolated. The glowing rivers of light that dominate the plane dissolve into a quieter darkness, punctuated only occasionally by dim, scattered stars. It is in this transition that one begins to appreciate just how fragile and delicate the galactic disk really is, like a luminous veil stretched across a much larger, darker canvas. This thinning of stars is not just a matter of visual beauty, but of structural significance. The disk itself contains the majority of the Milky Way's baryonic matter, ordinary matter made of protons, neutrons, and electrons, but beyond it, the gravitational scaffolding of the galaxy continues. Moving outward, luminous matter becomes increasingly scarce, and instead, we find the older and fainter populations of stars. These belong to the thick disk and the galactic halo, both of which extend above and below the plane. What astronomers find most striking about this region is not only the decrease in brightness, but also the shift in stellar composition. While the thin disk is populated by young, metal-rich stars still participating in the ongoing cycle of starbirth, these outer layers are populated by older, metal-poor stars, fossils of the galaxy's earliest eras. Their presence above and below the disk offers a glimpse into the Milky Way's distant past, long before it took its familiar spiral shape. The transition beyond the disk also reveals just how limited our naked eye view of the Milky Way really is. From Earth, embedded in the galactic plane, we see the thick river of stars stretched across the sky, but we rarely comprehend how quickly this density falls away once one travels vertically away from the plane. The decrease in luminous stars is so significant that the regions above and below appear nearly empty by comparison. Yet, these are not barren voids. They are layered with hidden structures, globular clusters, faint streams of stars from disrupted galaxies, clouds of hydrogen gas, and vast envelopes of dark matter that cannot be seen but make their presence felt through gravity. Above and below the crowded plane lies the quiet architecture of the Milky Way, less dazzling but essential for its stability. Astronomers measure this thinning by studying the scale height of the galactic disk. The thin disk, which contains most of the galaxy's visible stars, extends about 1,000 light-years above and below the plane. Beyond this, the thick disk emerges, stretching to several thousand light-years in height. This thick disk is populated with stars that are typically older, about 8 to 12 billion years old, and poorer in heavy elements, suggesting they formed early in the galaxy's history. Such populations act as time capsules, carrying with them the chemical fingerprints of the conditions that existed when the Milky Way was still in its formative years. The shift from the thin to the thick disk, and eventually into the halo, demonstrates that moving vertically through the galaxy is like peeling back layers of time itself. One of the remarkable discoveries about regions above and below the disk is the presence of stellar streams. These are long, faint trails of stars created when smaller dwarf galaxies venture too close to the Milky Way and are torn apart by its tidal forces. Their stars are stripped and spread out along elongated orbits, arcing far above and below the galactic plane. The Sagittarius stream is one of the most well-known examples, wrapping around the Milky Way in a vast, looping trail. These stellar streams are evidence of the galaxy's violent history of mergers and collisions, showing that the space above and below is not static emptiness, but a living record of galactic cannibalism. Another fascinating feature that becomes more prominent beyond the disk is the population of globular clusters. These ancient, tightly bound groups of stars orbit the galaxy in extended halos, distributed far above and below the galactic plane. Each cluster can contain hundreds of thousands of stars, and many of them are among the oldest stars in the universe, dating back over 12 billion years. Their positions above and below the disk act like markers, outlining the vast, spherical halo that encases the Milky Way. In this sense, while the stars thin out in density, the structures that remain grow in importance, revealing the hidden skeleton of the galaxy's architecture. It is also in these regions, above and below the galactic disk, that astronomers encounter signs of invisible matter shaping the galaxy's form. Dark matter, though undetectable by light, reveals its influence through gravitational effects. The very fact that stars and clusters exist so far above and below the disk, bound to the Milky Way, suggests that an enormous amount of unseen mass envelops the galaxy. Without it, these distant stars would drift away into intergalactic space. Thus, moving beyond the disk not only highlights the sparseness of visible stars, but also underscores the dominance of dark matter in defining the galaxy's true extent. Surrounding the Milky Way, and stretching far above and below the disk, lies one of the most mysterious and least visible components of our galaxy, the galactic halo. Unlike the bright flattened disk with its spiraling arms and nebulae, the halo does not dazzle with luminous beauty. Instead, it is a vast, ghostly sphere of influence, reaching tens of thousands of light years in every direction, encompassing the galaxy like an invisible bubble. To the naked eye, it appears non-existent, but its presence is undeniable, revealed through the distribution of ancient stars, the orbits of globular clusters, and the gravitational pull of elusive dark matter. If the galactic plane is the stage upon which the galaxy's drama unfolds, the halo is the unseen theater, its walls shaping the entire performance. The stellar component of the halo is one of its most intriguing aspects. Unlike the crowded thin disk where billions of stars cluster together, the halo's stars are incredibly sparse. They are scattered across enormous volumes of space, separated by vast distances that dwarf the gaps between stars in the disk. Many of these halo stars are metal-poor, meaning they lack the heavier elements forged in later generations of stellar evolution. This scarcity of metals reveals their age. Most halo stars are ancient, relics from the earliest days of the Milky Way, possibly dating back more than 12 billion years. These stars act as fossils, carrying within their light the chemical signatures of the primordial universe. They are not distributed in neat, orderly patterns, but instead drift through the halo on wide, eccentric orbits, crossing above and below the galactic plane over millions of years. Globular clusters form another defining feature of the halo. These tightly bound spherical groups of stars are scattered throughout the halo, orbiting the galaxy in wide arcs that extend far beyond the disk. Each globular cluster can contain hundreds of thousands or even millions of stars packed together so densely that in their cores, stars are separated by only fractions of a light year. They are among the oldest structures in the galaxy, some nearly as old as the universe itself. These clusters orbit not in the disk but within the halo, acting like luminous markers that map the boundaries of the galaxy's hidden sphere. Their very survival over billions of years speaks to the stability of their orbits and the gravitational influence of the halo itself. If the galactic plane is a snapshot of the galaxy's present, globular clusters above and below it are windows into its past. But the most dominant, though invisible component of the galactic halo is dark matter. Observations of the Milky Way's rotation reveal that the visible stars, gas, and dust account for only a fraction of the mass required to hold the galaxy together. The outer stars orbit too quickly to be explained by the gravitational pull of visible matter alone. The solution to this mystery lies in a vast, roughly spherical halo of dark matter, an invisible form of matter that does not emit or absorb light, but exerts gravitational force. This dark matter halo stretches far beyond the limits of the visible galaxy, possibly extending hundreds of thousands of light years above and below the disk. Without it, the Milky Way as we know it could not exist. Its spiral arms would fly apart, and its structure would unravel. The halo of dark matter is not only the largest component of our galaxy, but also its binding glue, holding everything together within its unseen grasp. The galactic halo is not uniform, but instead filled with substructures that tell the story of the Milky Way's evolution. Streams of stars, remnants of smaller galaxies torn apart by tidal forces, weave through the halo in intricate arcs. The Sagittarius stream, for example, is a colossal trail of stars left behind by the Sagittarius dwarf galaxy as it was gradually shredded by the Milky Way's gravity. These stellar streams cross above and below the galactic plane, like faint scars left behind by ancient cosmic battles. Each stream records an encounter, a merger, or a collision, showing that the halo is not an empty void, but a dynamic, ever-changing record of galactic growth. The halo is the graveyard of galaxies, where remnants of smaller systems are absorbed into the Milky Way, their stars redistributed into diffuse trails that stretch across the heavens. The gaseous component of the halo is equally fascinating. Astronomers have discovered that the Milky Way is surrounded by a corona of hot, ionized gas extending hundreds of thousands of light years above and below the disk. This galactic corona is so diffuse that it cannot be seen directly, but its presence is detected through X-ray observations and by studying how it absorbs light from distant quasars. This hot halo may contain as much mass as all the stars in the galaxy combined, and it could be the reservoir of the Milky Way's missing baryons, the normal matter that seems to be absent when astronomers count the stars and gas inside the disk. The corona represents a hidden ocean of matter, enveloping the galaxy in a faint, invisible glow. It is in this realm that the Milky Way interacts with its environment, exchanging material with intergalactic space and feeding the cycle of star formation within the disk. One of the most profound aspects of the galactic halo is its role in defining the true boundaries of the Milky Way. When people think of the galaxy, they often imagine the bright spiral disk and its glowing arms. But this is only the visible skeleton. The halo, stretching in all directions, is far larger, extending well beyond the visible disk. Its outer edges blend into intergalactic space, connecting the Milky Way to the larger structures of the local group and beyond. In this sense, the halo is not just an envelope around the galaxy, but the bridge between our home and the wider cosmos. The stars, globular clusters, streams, and dark matter it contains form the scaffolding upon which the entire Milky Way is built. Floating far above and below the galactic plane, embedded deep within the vast expanse of the Milky Way's halo, are some of the most ancient and remarkable stellar structures known to astronomy: globular clusters. These spherical groups of stars are not only breathtakingly beautiful, but also profoundly important to our understanding of the galaxy's past. Unlike the spiral arms of the disk, which are filled with young, vibrant stars and active star formation, globular clusters are fossil relics, survivors from the earliest eras of the universe. Their orbits extend high into the halo, sweeping through regions far beyond the crowded plane, and in doing so, they act like celestial lanterns, marking the boundaries of the Milky Way's invisible sphere. Where the disk fades and the halo becomes ghostly, globular clusters shine as beacons, giving structure and definition to the galaxy's outermost reaches. Each globular cluster is a marvel of density and stability. Containing anywhere from tens of thousands to millions of stars, they are gravitationally bound into tightly packed spheres. In their cores, the stars are so crowded that they can be separated by only a fraction of a light year, a level of density unimaginable in the thin disk of the Milky Way, where the nearest star to the Sun lies more than 4 light years away. Despite this crowding, globular clusters are incredibly stable, surviving for billions of years without dispersing. This stability has allowed them to persist from the earliest stages of galactic formation to the present day, serving as ancient archives of the conditions that prevailed in the young universe. One of the most striking features of globular clusters is their age. Many of them are estimated to be over 12 billion years old, nearly as old as the universe itself. This means that they formed before the Milky Way had even fully assembled into the spiral galaxy we know today. The stars within them are typically metal-poor, lacking the heavy elements created in later generations of stellar evolution. This chemical signature tells astronomers that globular clusters were born during a time when the universe was still dominated by hydrogen and helium, long before supernova had enriched the cosmos with carbon, oxygen, iron, and other heavy elements. In this sense, globular clusters are living fossils, containing some of the first stars to ever ignite. Their orbits are equally fascinating. Unlike stars in the galactic disk, which circle the center in relatively flat, ordered paths, globular clusters move along wide, eccentric orbits that carry them high above and below the plane. Some sweep out nearly spherical distributions around the galaxy, while others plunge through the disk on elongated trajectories. These orbits trace the true shape of the halo, revealing its spherical nature and extending far beyond the boundaries of the thin disk. In this way, globular clusters serve as signposts, marking the outer edges of the Milky Way, and showing that the galaxy is much larger than its luminous spiral arms suggest. Globular clusters are not evenly distributed, but are concentrated more heavily around the galactic center. This pattern provides clues to the history of the Milky Way's growth. Astronomers believe that many globular clusters were not formed in the Milky Way itself, but were instead captured from smaller galaxies that were torn apart and absorbed into the halo. Each cluster may carry the fingerprint of its origin, whether as part of a dwarf galaxy or as a relic of the Milky Way's earliest star-forming epochs. The presence of stellar streams, often associated with disrupted clusters and dwarf galaxies, reinforces this idea. The halo, with its globular clusters scattered across vast distances, is thus not merely an extension of the galaxy. It is the record of its violent and ongoing evolution. Studying globular clusters has also provided crucial insights into the size and age of the universe itself. Early in the 20th century, when astronomers like Harlow Shapley measured the distances to these clusters, they discovered that they were arranged in a spherical distribution around a point far away from the Sun. This was the first clear evidence that the Sun was not at the center of the universe, but rather that the Milky Way had its own central hub, with the Sun residing in its outskirts. Even today, globular clusters are used to refine measurements of cosmic distances and to calibrate our understanding of stellar evolution. Their stars, with well-understood life cycles, act as standard candles, helping astronomers to chart not just our galaxy, but also the broader universe. In the larger structure of the Milky Way, globular clusters are indispensable guides. They outline the edges of the halo, trace the history of galactic mergers, and illuminate the chemical fingerprints of the early universe. Rising far above and below the galactic plane, they remind us that our galaxy is not confined to the thin disk of stars visible in the night sky, but stretches outward into a vast, layered structure, much of it hidden from view. These clusters are the glowing breadcrumbs that lead us outward, pointing the way into the deeper mysteries of the halo, the corona, and the cosmic web beyond. While the thin disk of the Milky Way contains the majority of its stars, gas, and dust, there is another, less conspicuous structure that extends above and below it: the thick disk. This region is not as luminous or as densely populated as the thin disk, yet it carries within it a deeper story of the galaxy's origins. Stretching several thousand light-years above and below the galactic plane, the thick disk is home to older, dimmer stars whose chemical compositions and orbital behaviors preserve crucial clues about the early life of the Milky Way. If the thin disk is the galaxy's present, the bustling, ongoing cycle of star formation and stellar death, the thick disk is its memory, a fossil layer that connects us to an era when the Milky Way was still young, chaotic, and in the process of becoming what it is today. The distinction between the thin and thick disks arises not only from their vertical structure, but also from the types of stars they contain. The stars of the thick disk are typically older, often 8 to 12 billion years in age, compared to the younger populations in the thin disk. They are also less rich in heavy elements, or metals, in astronomical terminology. This suggests they formed at a time when the galaxy had not yet undergone enough cycles of supernova explosions to enrich the interstellar medium with heavier elements. In other words, thick disk stars reflect a more primitive stage of cosmic chemistry, when hydrogen and helium dominated, and elements like carbon, oxygen, and iron were still rare. By studying these stars, astronomers can peer into the chemical environment of the early Milky Way, reconstructing the processes that forged the first generations of stellar populations. Kinematics, the motions of stars, also reveal key differences between the thin and thick disks. Stars in the thin disk follow relatively circular orbits around the galactic center, remaining close to the plane as they move. Thick disk stars, on the other hand, have orbits that are more elliptical and tilted, carrying them higher above and below the plane. This gives the thick disk its greater vertical thickness, as its stars wander farther from the galactic midplane than their thin disk counterparts. Their orbits also tend to move more slowly around the center, further distinguishing them from the younger, faster stars of the thin disk. These differences in motion suggest that the thick disk was shaped by events far more turbulent than the calm star formation cycles of the thin disk. How the thick disk formed remains one of the great mysteries of galactic archaeology. Several theories have been proposed, each pointing to the tumultuous past of the Milky Way. One possibility is that the thick disk was created during an early merger with a smaller galaxy. Such an event would have stirred the stars of the Milky Way, scattering them into higher orbits above and below the plane. Another theory suggests that the thick disk represents the remnants of the Milky Way's earliest star-forming phase, when the galaxy was more compact and chaotic. Over time, as the thin disk formed from newly accreted gas, the older stars remained in their more extended, vertically dispersed orbits, creating the layered structure we see today. Still, another idea points to repeated gravitational interactions with passing dwarf galaxies, which could have heated the disk and puffed it up into its thickened shape. Regardless of the mechanism, the thick disk is a relic of the galaxy's violent youth, a reminder that the Milky Way has not always been the calm spiral we observe now. What makes the thick disk particularly fascinating is how it bridges the thin disk and the halo. In many ways, it serves as a transition zone between the dense, star-filled plane and the sparsely populated outer halo. Its stars are more metal-rich than those in the halo, but less enriched than those in the thin disk, placing them chronologically between the two. Their orbits also connect them to both regions, sometimes crossing into the halo's space while still belonging gravitationally to the disk. This transitional role makes the thick disk invaluable for understanding how the different components of the galaxy are related and how the Milky Way assembled itself over billions of years. Evidence for the thick disk only became clear in the latter half of the 20th century, when astronomers began carefully mapping the vertical distribution of stars and studying their velocities and chemical compositions. Prior to that, the Milky Way was thought of as consisting simply of a thin disk, a bulge at the center, and a surrounding halo. The discovery of the thick disk added a new layer to our understanding, literally and figuratively. It showed that the galaxy was not built all at once, but in stages, with overlapping populations of stars that tell a story of continual growth, mergers, and transformations. Today, thanks to data from surveys like Gaia, which measures the positions and motions of over 1 billion stars, astronomers can map the thick disk in unprecedented detail, uncovering patterns that reveal its dynamic history. As we move higher above and below the thin disk into the thick disk and beyond, the stars become scarcer, and the structures less obvious. But just beyond this region lies the realm where visible matter begins to give way almost entirely to the unseen, the vast dark matter halo that envelops the Milky Way from all directions. If the thick disk is a memory of the galaxy's formative years, then the dark matter halo is its invisible skeleton, a structure so immense and mysterious that it redefines the very notion of what lies above and below our galaxy. Invisible but crucial, dark matter forms a vast, roughly spherical halo that stretches well beyond the visible galaxy, enveloping the Milky Way from all sides and extending far above and below the familiar disk. If the spiral arms and glowing stars are the bones and flesh of the galaxy, then dark matter is its unseen skeleton, providing the gravity that holds the entire structure together. Without it, the Milky Way would not exist in its current form. The stars in the disk would spin out into intergalactic space, globular clusters would drift away, and the galaxy's delicate spiral would unravel. Dark matter may be invisible, but its presence is written into every motion, every orbit, and every ripple in the Milky Way's vast expanse. The discovery of the dark matter halo came not through direct observation, but through the puzzle of galactic rotation. When astronomers measured the orbital speeds of stars and gas at different distances from the galactic center, they expected to see the velocities decrease with distance, just as planets in the solar system move more slowly the farther they are from the sun. Instead, the rotation curve of the Milky Way remained flat. Stars on the outskirts orbited just as quickly as those closer to the center. The visible matter, stars, gas, and dust, simply did not account for the necessary mass to keep these outer stars bound. The only explanation was that an enormous amount of invisible matter must surround the galaxy, exerting gravitational influence on all sides. This revelation gave birth to the concept of the dark matter halo, a structure far larger and more massive than the luminous disk itself. The size of the dark matter halo is staggering. While the visible disk of the Milky Way is about 100,000 light-years across, the halo may extend as far as 300,000 to 1 million light-years in radius, blending eventually into the halos of neighboring galaxies like Andromeda. Its mass is even more astonishing. Estimates suggest that the Milky Way contains about 1 trillion times the mass of the Sun, and most of that mass lies not in stars or gas, but in the dark matter halo. This means that the galaxy we see, the stars, nebulae, and glowing arms, represents only the tip of a much larger iceberg. The true Milky Way, defined by mass rather than light, is far more immense and mysterious than our eyes or even telescopes can directly perceive. Despite its importance, dark matter itself remains one of the greatest unsolved mysteries of modern science. We know it is there because of its gravitational effects, but we do not know what it is made of. It does not emit, absorb, or reflect light, making it invisible across the electromagnetic spectrum. Current theories suggest that dark matter may consist of exotic particles, such as WIMPs, weakly interacting massive particles, or actions, which interact only through gravity and possibly the weak nuclear force. Yet, despite decades of searching with highly sensitive detectors deep underground and in space, no direct detection has yet been achieved. The halo remains an enigma, undeniably real in its effects, but elusive in its nature. Above and below the galactic disk, the dark matter halo provides the framework within which all other structures exist. Globular clusters orbit securely within its gravitational grip. Stellar streams, formed from torn-apart dwarf galaxies, arc across its vastness, their paths shaped by its invisible contours. Even the gas of the galactic corona and the movements of satellite galaxies like the Magellanic Clouds are governed by the silent pull of the halo. Without it, these structures would drift apart. The halo is not just a background feature. It is the stage, the boundaries, and the unseen force shaping everything we observe in the Milky Way and its surroundings. The spherical nature of the halo also changes how we think about the concepts of above and below the galaxy. While the disk gives us a clear orientation, the halo extends outward in all directions, enveloping the galaxy in a roughly spherical cocoon. To move above or below the plane is, in truth, simply to move deeper into the halo, into regions where dark matter dominates and luminous matter becomes increasingly scarce. The farther one travels away from the disk, the more the galaxy fades into shadow until what remains is almost entirely unseen mass, stretching into the silent depths of intergalactic space. Intriguingly, the dark matter halo is not thought to be entirely smooth. Computer simulations suggest it may contain substructures, clumps and filaments of dark matter that reflect the processes by which the Milky Way assembled itself. Some of these subhalos may still host faint dwarf galaxies or streams of stars, while others may exist purely as gravitational anomalies, invisible except for the way they subtly disturb the motions of stars and gas. By studying these disturbances, astronomers hope to map the halo more precisely, peeling back the layers of its invisible architecture. In this way, the halo is not simply a static envelope, but a living record of cosmic history, encoding the mergers, collisions, and flows of matter that gave birth to our galaxy. Beyond its role in shaping the Milky Way, the dark matter halo links our galaxy to the larger cosmic web. The Milky Way is not an isolated island, but part of the local group of galaxies, bound together by a network of dark matter filaments. The halo's outer regions likely overlap with those of Andromeda, setting the stage for the two galaxies' eventual merger billions of years from now. In this sense, the halo is both the boundary of the Milky Way and the bridge to its neighbors, a reminder that galaxies are not self-contained, but connected through the invisible threads of dark matter that span the cosmos. Above and below the familiar glow of the galactic disk, where stars grow sparse and the halo begins to dominate, astronomers have discovered something both strange and essential: vast, high-velocity clouds of hydrogen gas racing through the Milky Way's outer regions at astonishing speeds. These immense structures are not luminous like stars or clusters, nor are they ancient fossils like globular clusters. Instead, they are dynamic, fast-moving reservoirs of raw material, streams and blobs of neutral hydrogen gas that appear to be plunging into the Milky Way from intergalactic space. Their existence reminds us that the galaxy is not a closed system, but an open, evolving entity, constantly drawing in new matter from above and below, fueling its cycles of star formation and interacting with its cosmic environment. High-velocity clouds, or HVCS, are so named because they move at speeds far greater than the normal rotation of the Milky Way's disk, hundreds of kilometers per second faster than expected. These velocities immediately distinguish them from the ordinary gas clouds that orbit within the disk. Discovered in the mid-20th century through radio observations of the 21-centimeter emission line of neutral hydrogen, HVCS appeared as anomalous features in the sky, their motion unaccounted for by the galactic rotation curve. Over the decades, astronomers have mapped them in greater detail, revealing that they are scattered across the sky, with many located above and below the galactic plane. Some appear as small, isolated clouds, while others stretch into sprawling complexes spanning thousands of light years. The origin of these clouds is one of the most compelling mysteries of galactic astronomy. One hypothesis is that they represent leftover material from the formation of the Milky Way, primordial gas that never fully settled into the disk. Another possibility is that they are accreted streams from intergalactic space, material falling into the galaxy along dark matter filaments that connect the Milky Way to the cosmic web. Some HVCS may even come from the galaxy itself, expelled by supernova-driven winds or energetic outflows from the central regions, only to rain back down onto the disk in a cycle known as the galactic fountain. The truth is likely a mixture of all these processes, with HVCS reflecting the constant give and take between the Milky Way and its cosmic surroundings. One of the most famous examples is the Magellanic Stream, a colossal ribbon of hydrogen gas stretching more than 100,000 light-years across the sky, trailing behind the large and small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way. This stream arcs far above and below the galactic plane, wrapping around the halo and interacting with it as it falls toward the disk. The Magellanic Stream is a dramatic illustration of how satellite galaxies contribute material to the Milky Way, their gas stripped away by tidal forces and funneled into our galaxy's gravitational grasp. This enormous river of hydrogen may eventually feed the disk with enough fuel to power future generations of star formation, extending the life cycle of the galaxy itself. High-velocity clouds also play a critical role in solving one of the enduring puzzles of galactic evolution: how galaxies maintain their reservoirs of star-forming material over billions of years. Stars consume gas when they form, and without replenishment, galaxies would quickly exhaust their supplies. Yet the Milky Way, at over 13 billion years old, continues to produce new stars. HVCS may be the answer. By raining down onto the disk from above and below, they provide a steady influx of fresh hydrogen, sustaining the galactic ecosystem. In this way, they act as cosmic lifelines, ensuring that the cycle of star birth and death continues long after the original gas of the disk should have been depleted. The interaction between high-velocity clouds and the galactic halo is another area of intense research. As these fast-moving hydrogen clouds plunge through the hot, diffuse gas of the halo, sometimes called the galactic corona, they undergo complex processes of heating, stripping, and mixing. Some may be torn apart and absorbed into the halo before reaching the disk, while others may survive the journey, delivering their payload of gas to the star-forming regions below. These interactions are not only important for the Milky Way, but also for understanding galaxy formation in general, as they illustrate the mechanisms by which galaxies accrete new material and grow. Even though high-velocity clouds are mostly composed of hydrogen, they are not chemically uniform. Some show signs of being enriched with heavier elements, suggesting they originated in the Milky Way itself before being expelled into the halo. Others appear more pristine, closer in composition to primordial gas, which supports the theory that at least some HVCS are extragalactic in origin. By studying their chemical fingerprints, astronomers can trace their histories, distinguishing between material that has always belonged to the galaxy and gas that is being drawn in from the intergalactic medium. This blending of sources paints a picture of the Milky Way as a dynamic participant in a larger cosmic ecosystem, recycling its own material while constantly pulling in fresh supplies from the universe beyond. From Earth, we cannot see high-velocity clouds with our eyes, but their presence is revealed in radio observations, where the neutral hydrogen shines at the 21-centimeter wavelength. Modern surveys, including those using massive radio telescope arrays, have mapped these clouds in exquisite detail, showing their shapes, motions, and interactions with the halo. Some appear as compact, comet-like structures with tails of gas trailing behind them, evidence of their turbulent passage through the galactic corona. Others spread out into sprawling complexes, covering wide swaths of sky. Together they form a hidden network of gaseous flows above and below the Milky Way, invisible to human sight, but vital to the galaxy's continued existence. Surrounding the Milky Way in a vast, nearly invisible cocoon lies the galactic corona, a hot, diffuse halo of gas that stretches hundreds of thousands of light-years above and below the disk. Unlike the thin disk's dense clouds of cold hydrogen or the bright glow of star-filled arms, the corona is ethereal, tenuous, and extraordinarily extended, wrapping around the galaxy in all directions. It is a structure that cannot be seen with the naked eye and barely registers even in conventional telescopes. Yet, despite its ghostly nature, the galactic corona may hold one of the most important keys to solving a mystery that has puzzled astronomers for decades: the case of the Milky Way's missing matter. The corona is composed primarily of ionized gas, plasma heated to millions of degrees Kelvin. Because it is so hot and diffuse, it does not shine brightly in visible light, but instead emits faintly in X-rays and ultraviolet radiation. It was first detected not by being seen directly, but by its subtle influence on light from distant sources. When astronomers studied quasars and other galaxies beyond the Milky Way, they noticed that their light was being absorbed in characteristic patterns, indicating the presence of ionized oxygen and other elements. These absorption lines revealed that the Milky Way is enveloped in an enormous reservoir of hot gas, one that extends far beyond the disk and halo of stars, possibly out to half the distance between the Milky Way and Andromeda. The size of the corona is staggering. While the visible disk of the galaxy measures around 100,000 light-years in diameter, the corona may stretch 300,000 to 500,000 light-years outward, creating an envelope that dwarfs the luminous structures of the Milky Way. Its mass may be equally significant. For years, astronomers puzzled over why the Milky Way appeared to be missing much of its baryonic matter, the ordinary matter made of protons and neutrons that should account for a significant portion of its mass. While the stars, gas, and dust in the disk and halo are immense, they fall far short of the predicted total. The galactic corona may solve this puzzle. Estimates suggest it could contain as much as the combined mass of all the stars in the galaxy, hidden in this vast, diffuse reservoir of ionized gas. The corona does not exist in isolation, but plays an active role in the galaxy's life cycle. As high-velocity clouds plunge through it, they are buffeted, stripped, and heated, sometimes dissolving into the surrounding plasma and enriching it with heavier elements. Conversely, the corona may also cool and condense in localized regions, sending gas streaming downward to replenish the disk and fuel new generations of stars. This interplay between inflows and outflows, the galactic fountain, makes the corona not just a static reservoir, but a dynamic participant in the Milky Way's evolution. It acts as a buffer between the galaxy and intergalactic space, regulating the exchange of matter between the two, and ensuring that the Milky Way does not simply run out of star-forming material. The origins of the corona are deeply tied to the violent history of the galaxy. Some of its gas may be primordial, left over from the collapse of the protogalactic cloud that birthed the Milky Way over 13 billion years ago. Other parts may come from galactic winds, streams of hot plasma expelled from the disk by supernova explosions or energetic activity near the central black hole. Still more may have been acquired through interactions with neighboring galaxies, such as the Magellanic Clouds, which shed gas into the Milky Way's gravitational field. In this way, the corona is a patchwork, a layered record of billions of years of galactic history, with contributions from the galaxy's birth, its stellar processes, and its cosmic environment. Studying the galactic corona is an enormous challenge, precisely because it is so faint. Its density is incredibly low, only a few particles per cubic centimeter, compared to millions in the densest regions of the disk. Yet its sheer size makes its total mass immense. Astronomers use X-ray observatories like Chandra and XMM Newton, as well as ultraviolet instruments aboard the Hubble Space Telescope, to detect its presence indirectly. By analyzing how the corona absorbs or scatters light from distant objects, they can trace its composition, temperature, and structure. These observations reveal a halo that is not uniform but patchy, turbulent, and constantly in motion. A vast, simmering sea of hot plasma surrounding the galaxy on every side. Perhaps the most fascinating aspect of the corona is its role in connecting the Milky Way to the larger cosmic web. The edges of the corona likely blend seamlessly into the intergalactic medium, the thin gas that permeates the universe between galaxies. This means that the corona is not merely the Milky Way's outer boundary, but also its interface with the wider cosmos. Through it, the galaxy exchanges material with its environment, accreting fresh gas from cosmic filaments while simultaneously expelling enriched plasma from its interior. In this sense, the corona is both a shield and a gateway, insulating the galaxy from intergalactic emptiness while also linking it to the broader structures of the universe. Far above and below the galactic disk, hidden within the vast halo, lie some of the most hauntingly beautiful features of the Milky Way's architecture: streams of stars. These stellar streams are long, graceful ribbons of light, trails of stars that arc across the galaxy's halo, sometimes wrapping nearly all the way around it. They are not born in the Milky Way itself, but are the remnants of smaller dwarf galaxies and globular clusters that have ventured too close to our galaxy's immense gravitational pull. Over time, these smaller systems are shredded, their stars stripped away and stretched out into elongated currents. What remains is a cosmic tapestry of stellar trails that weave above and below the disk, silent records of the Milky Way's cannibalistic past. The formation of stellar streams is a direct result of tidal forces, the same gravitational interactions that cause tides in Earth's oceans, but on a vastly grander scale. When a dwarf galaxy or cluster falls into the Milky Way's gravitational field, the difference in gravitational pull across its structure begins to tear it apart. Stars on the leading edge are pulled forward, while those trailing behind are dragged back, and gradually the once compact system is stretched into a stream of stars orbiting the galactic center. These streams preserve the orbital paths of their progenitors, arcing high above and below the galactic plane as they trace their courses through the halo. One of the most famous examples is the Sagittarius Stream, a vast ribbon of stars that loops around the Milky Way in a nearly polar orbit. It is the remnant of the Sagittarius dwarf galaxy, which is currently being torn apart by the Milky Way's gravity. Parts of this stream pass above the galactic disk, while others dive below, forming a loop so immense that it encircles the galaxy. For astronomers, the Sagittarius Stream is a living laboratory for studying galactic mergers, providing a direct view of how the Milky Way consumes smaller galaxies and assimilates their stars into its halo. It is also a stark reminder that the galaxy we inhabit is not static or serene, but actively reshaping itself through cosmic collisions. Beyond Sagittarius, many other stellar streams have been discovered in recent years, thanks in large part to surveys like the Sloan Digital Sky Survey and the Gaia mission. Gaia, in particular, has revolutionized our understanding by mapping the motions of over 1 billion stars with extraordinary precision. Through Gaia's data, astronomers have identified dozens of faint streams crisscrossing the halo, each one the remnant of a disrupted dwarf galaxy or globular cluster. These discoveries have revealed that the halo is not a uniform, smooth envelope of stars, but a dynamic, tangled web of trails and debris, each one recording an ancient interaction. The study of stellar streams is not just about reconstructing the Milky Way's history, but also about probing the invisible dark matter halo that surrounds it. Because streams of stars are so delicate, their shapes and motions are exquisitely sensitive to the gravitational environment through which they pass. If the dark matter halo is smooth, streams should be long, continuous, and evenly distributed. But if the halo contains clumps of dark matter, as many theories predict, then streams may show gaps, kinks, or distortions where their paths were perturbed. By mapping these irregularities, astronomers can test the very nature of dark matter, using stellar streams as cosmic detectors of the unseen. What makes stellar streams especially fascinating is how they connect the Milky Way to the broader narrative of galactic evolution. Large spiral galaxies like ours did not form in isolation. They grew through a process of hierarchical assembly, absorbing smaller galaxies over billions of years. Streams of stars are the direct evidence of this process, the skeletons of galaxies past, still visible in the halo. Each stream is a remnant of a smaller world, once home to billions of stars, perhaps even planets and civilizations, that has now been consumed and scattered across the sky. In this sense, the halo is not just an extension of the Milky Way, but a graveyard of galaxies, with stellar streams as its epitaphs written in light. From Earth, stellar streams are faint and nearly invisible to the naked eye, but modern telescopes and surveys reveal them as ghostly arcs against the backdrop of space. Some stretch for tens of thousands of light years, their faint light barely detectable above the galactic glow. Others are more compact, looping tightly around the galaxy. Together, they create a hidden architecture above and below the disk, weaving a web of stellar debris that reveals the violent, ongoing process of galactic growth. To gaze upon these streams is to see the Milky Way, not as a finished structure but as a work in progress, still building itself through the destruction of others. Towering above and below the galactic plane, rising tens of thousands of light years into the halo, are two of the most astonishing and enigmatic features of the Milky Way, the Fermi bubbles. These enormous balloon-like structures, first discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope, stretch nearly 50,000 light-years in total, dwarfing the visible disk in their vertical reach. They are not visible in ordinary light, but in high-energy gamma rays they blaze as colossal lobes, symmetrically positioned above and below the galactic center. Their sheer scale and energy make them some of the most dramatic evidence that the Milky Way's core is far from dormant. Instead, these bubbles suggest that deep in the past, the supermassive black hole at the heart of our galaxy unleashed powerful eruptions that still echo through space today. The origin of the Fermi bubbles has become a central question in modern astrophysics. Their symmetry, centered on the galactic core, strongly indicates that they are linked to Sagittarius A, the Milky Way's central black hole, which weighs about 4 million times the mass of the Sun. Although it is relatively quiet now, astronomers believe that in the past it may have undergone episodes of violent activity, accreting vast amounts of gas and blasting out high-energy particles in twin jets. These jets could have inflated the bubbles, filling them with plasma that continues to radiate in gamma rays. In this scenario, the bubbles are scars of a galactic-scale outburst, evidence that our galaxy has an active past similar to quasars and radio galaxies observed in the distant universe. Another possibility is that the Fermi bubbles are not the result of black hole activity alone, but also of starburst events in the galactic center. The region surrounding the core is rich in stars, with many forming in dense, energetic clusters. A burst of rapid star formation, followed by an avalanche of supernova explosions, could have collectively expelled enough energy to drive gas out of the central regions, inflating the giant lobes. These starburst-driven winds are observed in other galaxies, where they create large-scale outflows that extend far into the halo. In the Milky Way, the Fermi bubbles may represent a combination of these two processes: the black hole's outbursts and the cumulative winds of dying stars working together to carve out these monumental structures. The physical characteristics of the bubbles make them even more intriguing. Each bubble contains plasma at millions of degrees, filled with high-energy electrons that emit gamma rays as they interact with surrounding photons. They also glow faintly in X-rays and microwave radiation, suggesting that they are not simple voids, but reservoirs of hot gas and energetic particles. Their sharp edges are particularly puzzling. Rather than fading gradually, the boundaries of the Fermi bubbles are distinct, as if the outflows that created them were contained by some kind of cosmic pressure. This sharpness implies that the event that generated them was sudden and violent, a burst of activity that rapidly inflated the structures and then subsided, leaving behind their vast outlines as echoes of that moment. Measuring the age of the Fermi bubbles has proven challenging, but current estimates suggest they may be between a few million and tens of millions of years old, young by galactic standards. If true, this would mean that the eruption that created them happened long after the Milky Way had already taken on its spiral structure, and long before humanity began gazing at the stars. In cosmic terms, they are recent events, suggesting that Sagittarius A is not entirely dormant, but capable of awakening with bursts of immense power that alter the very structure of the galaxy. The possibility that our central black hole could flare up again in the future adds a dramatic sense of immediacy to their study. The Fermi bubbles are also a window into the exchange of matter between the Milky Way and intergalactic space. They represent a massive outflow of energy and particles from the galactic core, carrying material far into the halo. This process may play a crucial role in regulating star formation, preventing the central regions of the galaxy from collapsing under their own density of gas and stars. By blowing out gas, the bubbles may act as a kind of galactic pressure valve, redistributing energy and matter above and below the plane, and even interacting with the surrounding galactic corona. In this way, they link the activity of the central black hole to the evolution of the galaxy as a whole. What makes the Fermi bubbles especially remarkable is how they reveal the Milky Way's hidden dynamism. To most of us, our galaxy appears serene, a quiet spiral turning gently in space, its stars moving in stately orbits. But the bubbles remind us that beneath this calm exterior lies a history of violence, eruptions, and transformation. They are the footprints of immense forces operating on scales almost beyond comprehension, forces that shape not just the core of the Milky Way, but the very structure of space above and below it. When we talk about what lies above and below our galaxy, it helps to define those directions clearly, and that is precisely what the north and south galactic poles provide. These 2 points, extending perpendicularly from the flat disk of the Milky Way, mark the directions directly above and below the galactic plane. Much like Earth's geographic poles give us a reference frame for north and south, the galactic poles give astronomers a way to orient the entire Milky Way within the universe. They are not physical structures. There are no great clusters or nebulae specifically attached to them, but they are conceptual beacons, mathematical definitions, that help us map our galaxy's position and study its relationship to the cosmos around it. The galactic coordinate system, developed to bring order to the vastness of the Milky Way, uses these poles as anchors. In this system, the center of the Milky Way, the point near Sagittarius A in the constellation Sagittarius, defines the origin of galactic longitude, while the galactic plane defines latitude. The North Galactic Pole, NGP, sits 90 degrees above the plane, while the South Galactic Pole, SGP, sits 90 degrees below, directly opposite. The NGP is located in the constellation Coma Berenices, while the SGP lies in Sculptor. From Earth, if one could look toward the NGP, the Milky Way's disk would be seen edge-on below, revealing the galaxy as a thin, bright line against the backdrop of intergalactic space. What makes the galactic poles so important is their role in helping us distinguish between what belongs to our galaxy and what lies beyond it. Looking along the plane, we see the crowded river of stars, dust, and gas that makes up the Milky Way's disk. But when we look toward the poles, we peer directly away from this cluttered band into the sparse halo and, eventually, into the realm of other galaxies. Surveys of the sky often make use of these directions, since observing near the poles provides a clearer, less obstructed view of the universe. The famous Hubble Deep Field, for example, was chosen near the galactic poles precisely because there is less interference from the Milky Way's stars and dust. Thus, the poles are not just abstract coordinates, they are gateways to exploring the larger universe. From a symbolic perspective, the galactic poles also remind us that the Milky Way is not an isolated frame of reference, but part of a greater cosmic geometry. Just as Earth's north and south poles orient us on our planet, the galactic poles orient us in space, allowing astronomers to measure the motions of stars, the tilts of stellar streams, and the orientation of satellite galaxies. When astronomers say a globular cluster or a dwarf galaxy orbits above or below the disk, they are describing it relative to these poles. Without them, our descriptions of galactic structure would be vague and inconsistent. With them, we have a precise system, allowing us to trace everything from the paths of high-velocity clouds to the towering outlines of the Fermi bubbles. There is also a poetic beauty in thinking of these poles as vantage points. If one could rise high enough to look straight down from the North Galactic Pole, the Milky Way's spiral arms would unfold in their full glory, their barred core and sprawling arms forming the grand pinwheel structure that is otherwise hidden from us within the disk. Conversely, looking up from the South Galactic Pole would provide the same cosmic portrait, only from the opposite side, offering a perspective that we can only imagine but not yet physically attain. These poles, then, are not only mathematical markers, but imagined observation posts, cosmic mountaintops from which the Milky Way would reveal itself in full. Above and below the galaxy, the North and South Galactic Poles serve as more than just points in space. They are conceptual tools that allow astronomers to define orientation, map structure, and expand perspective. They remind us that even though we are trapped within the plane, blinded by the dust and light of nearby stars, we can still imagine and mathematically construct the vantage points from which our galaxy's true form would be revealed. In doing so, the poles link the idea of above and below, not only to physical structures but also to the deeper human need to find direction in the infinite cosmos. If you could rise far above the Milky Way, escaping the crowded disk and the hazy veil of interstellar dust that blinds us from within, the view would be nothing short of breathtaking. From such a vantage point, the spiral structure of our galaxy would finally unfold in full, no longer a band of scattered stars across the sky, but a vast organized pinwheel of light. The Milky Way would stretch across space as a barred spiral galaxy, its central bar cutting across the bulge at the core, and its arms spiraling outward in sweeping arcs of stars, gas, and dust. Seen from above, it would resemble the grand design galaxies we observe elsewhere in the universe, like Andromeda's neighboring cousins or the iconic Whirlpool Galaxy. And yet, this would not just be another spiral galaxy, it would be our home, our island of stars adrift in the cosmic sea. The most striking feature from such an extragalactic view would be the spiral arms themselves. These are not solid structures, but density waves, ripples in the galactic disk that compress gas and dust as they move through it, triggering waves of star formation. In these arms, brilliant clusters of hot, young stars shine blue-white against the darker backdrop, while glowing nebulae mark the cradles of stellar birth. From our position inside the disk, these arms are difficult to trace, obscured by perspective and dust, but from above, their symmetry would become apparent. The Perseus arm sweeping wide on one side, the Scutum Centaurus arm curling tightly near the center, and the Orion spur, the small segment where our sun resides, nestled quietly between them. Our solar system, so vast to us on human scales, would appear as a mere speck in this grand design, lost in the brilliance of hundreds of billions of stars. At the heart of the galaxy, the central bulge would blaze as a concentrated glow of light, spherical and dense, packed with older stars. Cutting through this bulge would be the Milky Way's central bar, a stretched structure of stars and gas that channels material inward, feeding both the star formation in the bulge and the supermassive black hole, Sagittarius A, at the galaxy's core. From above, the bar would stand out clearly, extending tens of thousands of light-years across the center, anchoring the spiral arms that emerge from its tips. For astronomers, seeing the galaxy in this way would resolve debates that persist even now about the precise shape and number of the Milky Way's arms, something that remains uncertain due to our embedded perspective inside the disk. The outer disk, too, would reveal details invisible from within. Beyond the bright arms lies a more diffuse region where the density of stars decreases and the galaxy gradually blends into the halo. From above, one would see not only the spiral pattern but also the subtle warp in the disk, caused by gravitational interactions with satellite galaxies like the Sagittarius Dwarf and the Magellanic Clouds. The disk is not perfectly flat. It bends and twists, giving the Milky Way a slightly distorted, rippled appearance, like a vinyl record warped by heat. From Earth, we can only detect this warp indirectly, but from high above, it would be unmistakable, a reminder that our galaxy is not static, but shaped by constant interactions with its neighbors. If one were to rise even higher, to see not just the galaxy itself but its surroundings, the view would broaden into something even more humbling. Around the Milky Way, dozens of dwarf galaxies would become visible, many of them strung out in faint arcs and streams as they orbit or are consumed by the larger galaxy. The large and small Magellanic Clouds would shine brightly as irregular companions below the disk, their tidal tails feeding streams of gas into the halo. Other dwarfs, like the Fornax and Sculptor galaxies, would appear as faint smudges of light in the darkness, circling their massive host. These companions would reveal the Milky Way's role not as an isolated spiral, but as the dominant member of a small galactic family, constantly interacting with and absorbing its satellites. Perhaps the most awe-inspiring aspect of the extragalactic view would be the sense of scale. From Earth, the Milky Way dominates the night sky, appearing infinite in its span. But from above, one would see its finite edges, its disk tapering off into the emptiness of intergalactic space. Its spiral arms, though vast, would be clearly bounded, and beyond them would lie darkness, punctuated only by the faint glimmers of neighboring galaxies. This perspective would place the Milky Way in context, not as the universe itself, as ancient peoples once believed, but as one of countless galaxies, each with its own structure, history, and mysteries. Rising above the disk would transform our understanding of our place, showing us that the river of light we see overhead is but a single whirlpool in a cosmic ocean. Astronomers have long sought to reconstruct this extragalactic view of the Milky Way, using indirect methods. By mapping the positions of stars, gas clouds, and star-forming regions within the disk, and by comparing these with observations of other galaxies, scientists have pieced together an approximate picture of our home's spiral structure. Radio observations of hydrogen gas have been especially crucial, allowing astronomers to trace the spiral arms even where dust obscures visible light. Space telescopes like Spitzer and Gaia have added more detail, revealing the locations of billions of stars and refining our sense of the Milky Way's shape. Yet, despite all this progress, our map is still incomplete, and uncertainties remain about the exact number of spiral arms, their extent, and their connections to the central bar. From above, all these questions would be answered in a single glance. Above and below the luminous disk of the Milky Way, scattered across the vast envelope of the galactic halo, drift a collection of smaller stellar systems bound to our galaxy by gravity, the satellite galaxies. These companions, though faint compared to the grandeur of the Milky Way itself, play an essential role in shaping its evolution. They orbit like moons around a planet, tethered to the Milky Way's immense gravitational field, their paths weaving far above and below the disk. Some are massive enough to be visible to the naked eye, like the large and small Magellanic Clouds, while others are ghostly dwarfs, barely discernible against the background of the cosmos. Together they form a kind of galactic entourage, smaller, dependent companions gradually being pulled apart and absorbed into the larger system they orbit. The most prominent of these companions are the Magellanic Clouds, two irregular dwarf galaxies that orbit the Milky Way in tandem. The Large Magellanic Cloud, LMC, about 160,000 light-years away, is the most massive and luminous satellite of the Milky Way, while the Small Magellanic Cloud, SMC, located about 200,000 light-years away, is smaller but still significant. Both galaxies can be seen with the naked eye from the southern hemisphere, appearing as faint, cloudy smudges against the night sky. These two dwarfs are not only visually striking, but also scientifically crucial. Their interaction with the Milky Way has created tidal features such as the Magellanic Stream, a colossal river of gas that stretches over 100,000 light-years, arcing above and below the disk. This stream represents material stripped from the clouds by the Milky Way's gravity, now falling inward to fuel future star formation in our galaxy. In this way, the Magellanic Clouds act as both companions and donors, enriching the Milky Way even as they are slowly dismantled. Beyond the Magellanic Clouds, the Milky Way is surrounded by a host of smaller dwarf galaxies, many of which have only been discovered in recent decades thanks to deep sky surveys like the Sloan Digital Sky Survey and the Gaia mission. These dwarfs are far dimmer than the clouds, often containing only a few million stars, tiny by galactic standards, yet still bound tightly by dark matter halos. Examples include the Fornax, Sculptor, Carina, and Draco dwarfs, each located tens to hundreds of thousands of light-years from the Milky Way's center. Many of these galaxies are so diffuse that they blend into the night sky, detectable only through careful statistical analysis of star distributions. Yet, despite their faintness, they are crucial for understanding the Milky Way's growth, as they represent the building blocks from which larger galaxies are assembled. Indeed, the story of satellite galaxies is one of gradual assimilation. The Milky Way, like all large galaxies, has grown not solely by forming stars internally, but also by cannibalizing smaller systems. The stellar streams we observe in the halo are the debris of past mergers, remnants of dwarf galaxies torn apart by tidal forces. The Sagittarius dwarf galaxy is a prime example of this process, currently being shredded as it plunges through the disk. Its stars are stretched into long arcs that wrap above and below the plane, slowly blending into the halo as the dwarf itself is consumed. Over billions of years, many of the Milky Way's current satellites will meet the same fate, their stars redistributed into the halo while their gas is siphoned into the disk. The halo is, in many ways, a graveyard of galaxies, littered with the remains of countless smaller companions that came too close. The orbits of satellite galaxies are themselves fascinating, often highly inclined relative to the galactic plane. Some orbit nearly perpendicular to the disk, tracing long arcs above and below, while others move along paths that cut through the halo. Their distribution is not random. Recent studies suggest that many of the satellites may be aligned in a vast rotating plane around the Milky Way, a structure that challenges standard models of galaxy formation. This unexpected organization hints at a more complex history of how the Milky Way acquired its companions, possibly through the accretion of groups of galaxies rather than individual dwarfs. Such findings remind us that the halo above and below the disk is not simply a region of scattered stars, but a dynamic environment where entire galaxies interact, orbit, and dissolve. Satellite galaxies are also invaluable for probing the invisible dark matter halo of the Milky Way. Because they are so faint and so dominated by dark matter, their motions are highly sensitive to the gravitational environment. By studying their orbits, astronomers can map the mass distribution of the halo, including its outermost regions, which are otherwise inaccessible. The survival of some satellites and the disruption of others provide further clues about the shape and extent of the halo, revealing whether it is smooth or clumpy, spherical or elongated. In this sense, the satellites are not just passive companions, but active tracers of the Milky Way's hidden skeleton. Perhaps most poignantly, satellite galaxies remind us of the scale of cosmic evolution. Just as the Milky Way itself will one day merge with Andromeda, so too are these smaller galaxies fated to merge with us. Over the next billions of years, the Magellanic Clouds, Fornax, Sculptor, and countless others will gradually dissolve, their stars joining the halo, their gas fueling new bursts of star formation in the disk. Above and below the plane, the faint glimmers of these dwarfs are not permanent fixtures, but fleeting stages in a much larger cycle of growth and assimilation. The Milky Way, majestic though it seems, is still assembling, still feeding on its companions, still evolving into something larger and more complex. From our vantage point within the disk, the satellite galaxies are difficult to appreciate in their full context. But if one could rise above, the picture would be clear. The Milky Way encircled by a swarm of smaller companions, some bright and robust like the Magellanic Clouds, others ghostly and fading into dissolution. Together, they form the outermost layer of our galactic system, the boundary between the Milky Way and intergalactic space. They remind us that above and below the galaxy are not empty voids, but regions alive with smaller galaxies, tethered by gravity and slowly merging into the vast spiral we call home. Above and below the Milky Way's disk, stretching far into the halo and beyond, lie some of the most delicate and haunting structures in our cosmic neighborhood, intergalactic bridges. These are vast rivers and filaments of gas, primarily hydrogen, that connect the Milky Way to nearby galaxies, weaving invisible threads through the darkness of intergalactic space. They are not luminous like stars, nor dense enough to form galaxies of their own, but their presence reveals a truth that is both profound and humbling. The Milky Way is not an isolated island adrift in emptiness, but part of a connected network of matter. Through these bridges, our galaxy exchanges material with its companions, interacts with its environment, and participates in the grander structure of the local group. The most famous and striking of these bridges is the Magellanic Stream. This enormous ribbon of neutral hydrogen gas stretches more than 100,000 light-years across the sky, arcing above and below the Milky Way. It trails behind the large and small Magellanic Clouds, our two most prominent satellite galaxies, like a vast cosmic tail. Formed through tidal interactions and ram pressure as these dwarfs orbit the Milky Way, the stream is a direct bridge of material flowing between galaxies. Some of it is stripped from the Magellanic Clouds, while other parts may be funneled into the Milky Way, eventually raining down into the disk as fresh fuel for star formation. The Magellanic Stream demonstrates that the halo above and below the galaxy is not empty, but alive with currents of gas that bind galaxies together in an intricate dance of matter and gravity. Complementing the Magellanic Stream is the Leading Arm, another vast bridge of gas stretching ahead of the Magellanic Clouds in their orbit. If the stream is the trailing wake of these dwarfs, the Leading Arm is their forward bow wave. It arcs far into the halo above the galactic disk, curving toward the Milky Way as though heralding the arrival of its companion galaxies. Together, the Magellanic Stream and Leading Arm form a kind of double tether, tying the clouds to the Milky Way through threads of gas that span tens of thousands of light-years. These bridges are both the evidence of tidal disruption and the promise of replenishment, as the Milky Way draws in material from its companions to sustain its life cycle. But the Magellanic features are not the only intergalactic bridges linking our galaxy to others. Observations have revealed tenuous filaments of hydrogen gas stretching between the Milky Way and other members of the local group, including Andromeda, M31, and Triangulum, M33. Though faint, these bridges hint at a deeper connection between the major galaxies of our neighborhood. The Milky Way and Andromeda in particular appear to share a diffuse bridge of hot, ionized gas, detectable through the way it absorbs light from more distant quasars. This bridge is not a narrow stream, but a sprawling envelope, extending hundreds of thousands of light-years above and below both galaxies, blending their halos together. It foreshadows the eventual merger of the Milky Way and Andromeda, showing that the two galaxies are already interacting, exchanging matter across the intergalactic gulf. These bridges are also important clues to the larger cosmic structure known as the cosmic web. On the grandest scales, galaxies are not randomly scattered but arranged along filaments of gas and dark matter that connect clusters across the universe. The intergalactic bridges in the local group can be seen as smaller versions of these filaments, scaled down to the neighborhood of our galaxy. They reveal that even at the scale of a few 100,000 light-years, galaxies are bound together not just by gravity, but also by flowing streams of matter that move along invisible highways through space. The gas above and below the Milky Way is thus not isolated but part of a continuum that stretches outward into the web of the universe. What makes intergalactic bridges so intriguing is their role in galactic evolution. Gas is the raw material of star formation, and without new supplies, galaxies eventually run dry. The streams and bridges that connect the Milky Way to its companions act as lifelines, delivering fresh hydrogen into the disk and sustaining the galaxy's star-forming activity. At the same time, they also represent loss, as material is stripped from satellites and siphoned into the Milky Way's grasp. This cycle of accretion and stripping is part of the larger story of galactic cannibalism, where large galaxies grow by feeding on smaller ones. Above and below the Milky Way, the intergalactic bridges are the visible evidence of this process, the highways along which matter flows as galaxies merge and evolve. From Earth, these structures are invisible to the eye, but radio telescopes tuned to the 21-centimeter emission line of hydrogen have mapped them in detail. These maps reveal the astonishing extent of the Magellanic Stream and other gaseous filaments, showing how they arc across the sky and intertwine with the Milky Way's halo. Ultraviolet and X-ray observations add further detail, showing how these cold hydrogen rivers interact with the hot plasma of the galactic corona, heating, mixing, and sometimes fragmenting into smaller clouds. This complex interplay ensures that the bridges are not static, but dynamic, constantly changing as they move through the galaxy's environment. Beyond the glowing arms of the Milky Way, past the reach of its stellar halo, and even farther than the tenuous outlines of its gaseous corona and dark matter cocoon, lies a realm that is perhaps more mysterious than all the structures we've seen so far. The cosmic voids. These are not filled with stars, streams, or clusters. Instead, they are vast expanses of near-nothingness, stretching above and below the galaxy in all directions, where matter becomes astonishingly sparse and silence dominates. If the galactic plane and halo are alive with activity, stars orbiting, gas flowing, dark matter binding, then the voids are the opposite. Vast cosmic deserts where almost nothing stirs. They are the negative spaces of the universe, shaping everything by their very emptiness. Cosmic voids are some of the largest structures in the universe, though structures may seem a strange word to describe emptiness. Typically spanning tens to hundreds of millions of light-years across, voids are immense bubbles in the cosmic web, the vast lattice of filaments and clusters that defines the large-scale structure of the universe. The Milky Way, like all galaxies, does not exist inside one of these voids, but rather on the edges of them, nestled within filaments of the cosmic web. Yet, above and below the galactic disk, beyond the halo, we inevitably peer into the great expanses of these voids, into regions where galaxies are few and matter is spread so thin that for millions of light-years, there may be almost nothing at all. The contrast between the crowded galactic disk and the emptiness of the voids is staggering. Within the disk, stars may be separated by only a few light-years, while in voids, the distances between galaxies can be tens of millions of light-years or more. These regions are not absolutely empty. There is always some diffuse hydrogen gas, traces of dark matter, and perhaps faint dwarf galaxies scattered here and there. But compared to the bustling hubs of galaxy clusters, voids are ghost towns. They are defined less by what is in them than by what is missing. The absence of the bright, starry structures that dominate the rest of the cosmos. Why do such vast voids exist? The answer lies in the way the universe evolved after the Big Bang. In the first moments of cosmic time, matter was distributed almost uniformly, but tiny quantum fluctuations created slightly denser and slightly emptier regions. Over billions of years, gravity amplified these differences. Dense regions attracted more matter, collapsing into filaments, clusters, and galaxies, while the emptier regions grew emptier, expanding into cosmic voids. Today, the universe resembles a cosmic foam, dense filaments and walls of galaxies enclosing enormous bubbles of near-nothingness. The Milky Way, residing in the local group, lies along one of these filaments, and when we look above and below our galaxy, we are peering into the edges of these immense voids. One of the most famous examples is the local void, a vast region adjacent to our own local group. Spanning over 100 million light-years, the local void is a cosmic cavern almost entirely empty of galaxies, extending beyond the Milky Way's halo in one direction. Our galaxy and its neighbors sit on its boundary, drawn toward denser regions on one side, while pushed away from the void's emptiness on the other. In a sense, voids help direct the flows of galaxies across the universe. They are not passive regions, but dynamic players in cosmic evolution, their emptiness exerting a kind of gravitational influence that shapes the motions of galaxies around them. Voids are also important laboratories for understanding the universe's hidden physics. Because they contain so little matter, they are less affected by complex astrophysical processes like star formation, supernova explosions, or black hole activity. This makes them pristine environments for testing the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. By studying how voids expand and evolve, astronomers can place constraints on the properties of dark energy and even test alternative theories of gravity. In this way, the emptiness above and below the galaxy becomes a tool for probing the deepest mysteries of cosmology. Despite their emptiness, voids are not without subtle traces of structure. Within them, astronomers have found faint dwarf galaxies, sometimes isolated, like stranded wanderers in a desert. These void galaxies often look different from those in crowded clusters. They are more irregular, less massive, and often still-forming stars, having been spared the disruptive interactions that occur in denser environments. They are lonely, but in their loneliness lies uniqueness, offering glimpses of how galaxies evolve in isolation. Above and below the Milky Way, scattered across the voids, these faint galaxies whisper of resilience in the face of cosmic emptiness. From a human perspective, voids are almost impossible to imagine. To look into one is to confront distances so immense and spaces so barren that they defy intuition. Standing on Earth, we are surrounded by stars, planets, and galaxies, but beyond the halo, when one peers into the dark between filaments, the universe becomes shockingly quiet. The nearest galaxy might lie tens of millions of light-years away, and in between, there is almost nothing but sparse hydrogen atoms drifting alone through space. If the galactic disk is a bustling city and the halo its suburbs, then the voids above and below are the wilderness, vast, empty expanses where silence reigns supreme. Yet, these voids are not to be dismissed as empty in a trivial sense. Their very existence is essential to the universe's architecture. They provide the negative space that defines the cosmic web, just as the gaps between threads define the shape of a net. Without voids, the universe would not have the same balance of filaments and clusters. Galaxies would not flow along streams into denser regions. Above and below the Milky Way, the voids remind us that absence is just as important as presence, that emptiness is as much a part of the universe's structure as the galaxies themselves. So, when we ask what lies beyond the halo of the Milky Way, above and below its luminous disk, the answer is not always more stars or more galaxies. Sometimes the answer is silence, vastness, and near-nothingness. Cosmic voids are the quiet expanses that cradle the filaments of the cosmic web, the background against which the drama of galaxies unfolds. They are the universe's breath between words, the spaces that give meaning to the structures we see. In their emptiness, they speak of the cosmos on its grandest scale, reminding us that the Milky Way is not suspended in a crowded sky, but floats on the edge of great dark seas of nothingness. Above and below the Milky Way, hidden in the vast expanses of intergalactic space, the invisible hand of gravity is always at work. While the halo, the corona, and even the cosmic voids define the galaxy's immediate environment, it is the pull of other galaxies, especially our massive neighbor Andromeda, that profoundly shapes the way the Milky Way moves and evolves. Gravity does not stop at the edges of the disk or even the halo. It stretches outward endlessly, binding galaxies into groups, groups into clusters, and clusters into superclusters. The Milky Way is not an isolated island, drifting alone in silence. It is constantly tugged, tilted, and guided by the gravity of the galaxies that surround it, their combined influences pulling on it from above, below, and all directions of the cosmic web. The most significant of these influences comes from Andromeda, M31, the largest member of the local group of galaxies. Located about 2.5 million light-years away, Andromeda is roughly equal in mass to the Milky Way, perhaps even slightly larger, with a disk more expansive and a halo stretching hundreds of thousands of light-years. Its gravitational pull on the Milky Way is immense. Both galaxies are moving toward one another at a speed of roughly 110 kilometers per second, drawn together by their mutual attraction. From above or below the Milky Way, one could see these two spirals locked in a cosmic embrace, orbiting a common center of mass as they spiral closer together. Their eventual collision, predicted to occur in about 4 to 5 billion years, will merge them into a single giant elliptical galaxy. The gravitational pull of Andromeda is not just shaping our future, it is already shaping our present, subtly altering the orbits of stars, streams, and satellite galaxies above and below the Milky Way. Andromeda is not the only galaxy exerting its influence. The local group contains dozens of smaller galaxies, many of which orbit either the Milky Way or Andromeda. Each of these galaxies, from the Magellanic Clouds to faint dwarfs like Sculptor and Fornax, adds its gravitational fingerprint to the Milky Way's motion. Above and below the galactic plane, stellar streams like those of the Sagittarius dwarf galaxy trace the aftermath of these gravitational interactions, recording how smaller companions are torn apart and absorbed. These interactions are not random, but part of a larger ballet of galaxies orbiting within the gravitational field of the local group. Our galaxy is constantly nudged, tilted, and rebalanced by the gravity of its neighbors, reminding us that even a massive spiral like the Milky Way cannot move untouched through space. On even larger scales, the Milky Way is influenced by structures far beyond the local group. The local group itself is falling toward the Virgo Cluster, a massive concentration of galaxies located about 50 million light-years away. This infall is part of a broader gravitational flow toward the so-called Laniakea Supercluster, a colossal region spanning hundreds of millions of light-years that contains our local group along with many others. Above and below the Milky Way, the motions of galaxies are not random, they are guided by the gravitational wells of these immense structures. The Milky Way is pulled not just by Andromeda, but by the combined gravity of thousands of galaxies, all interlinked within the cosmic web. Interestingly, the absence of matter in nearby cosmic voids also shapes the galaxy's trajectory. Just as dense regions of the universe pull galaxies toward them, underdense regions, voids, push galaxies away. The local void, a vast region of near-nothingness adjacent to our local group, exerts a kind of repulsive influence, not through force but through the relative absence of gravitational pull. This void, stretching above and below the galactic disk, contributes to the overall motion of the Milky Way by leaving it free to be drawn more strongly toward denser regions on the opposite side. Thus, both presence and absence shape the way our galaxy moves, with voids and clusters together, carving out the pathways along which galaxies drift through space. The gravitational influences above and below the Milky Way are also written into the behavior of its halo. The stellar streams that arc across it, the motions of globular clusters, and the tilts of satellite galaxies all reflect the larger gravitational context. For example, the Magellanic Clouds are not only orbiting the Milky Way, but are also being pulled by Andromeda's halo. This three-way tug-of-war creates complex motions in the streams of gas that connect them to our galaxy. Likewise, the orbits of distant globular clusters may be subtly shifted by the gravitational pull of neighboring galaxies, creating distortions in their paths that reveal the invisible hand of intergalactic gravity. For humanity, perhaps the most dramatic implication of these gravitational influences is the coming collision with Andromeda. From our limited perspective on Earth, this event lies billions of years in the future, but in cosmic terms, it is already underway. The halos of the two galaxies are likely already touching, their outermost stars and gas clouds beginning to mingle above and below the disks. Over time, tidal forces will stretch both galaxies into streams and tails, flinging stars above and below the plane in chaotic arcs. Eventually, the two spirals will merge, forming a massive elliptical galaxy that will dominate the local group. Above and below the Milky Way, the quiet halo we see today will one day blaze with the fireworks of colliding galaxies, reshaped by gravity into something entirely new. The Milky Way, for all its grandeur and vastness, does not exist in splendid isolation. It belongs to a cosmic neighborhood known as the local group, a gravitationally bound collection of more than 50 galaxies spread across a region about 10 million light-years in diameter. Above and below the galactic plane, this collection of companions populates the space around us, forming a loose but interconnected community of galaxies that share both a common fate and a common gravitational well. To see the Milky Way within this context is to recognize that our galaxy is not a solitary island, but one of many members in a small cluster drifting together through the universe. At the heart of the local group are its two dominant members, the Milky Way and the Andromeda Galaxy M31. Roughly equal in mass, they are the gravitational giants around which most of the other galaxies orbit. Between them lies the Triangulum Galaxy, M33. The third largest member of the local group, smaller but still a substantial spiral in its own right. Together, these three galaxies form the core of the local group, their combined gravity holding dozens of dwarf galaxies in orbit around them. Above and below the disk of the Milky Way, these dwarfs appear scattered across the sky, each one a faint echo of galactic evolution, some still intact, others already being consumed. The dwarf galaxies are especially numerous. Some, like the large and small Magellanic Clouds, are visible to the naked eye and have rich histories of interaction with the Milky Way. Others, like Draco, Ursa Minor, and Sculptor, are so faint that they blend into the starry background, detectable only through careful surveys. Many of these dwarfs orbit above and below the Milky Way's disk, forming a kind of spherical cloud of companions embedded within the larger halo. Each one has its own unique structure. Some are irregular, shaped by gravitational tides. Others are spheroidal, little more than faint smudges of stars. Collectively, they serve as living fossils, preserving the conditions of galaxy formation in environments untouched by the violence of larger galaxies. From above, the local group itself would appear as a loose cluster, with the Milky Way and Andromeda dominating opposite sides of its gravitational field. The two spirals are on a slow but inevitable collision course, drawing not only themselves but also their satellite galaxies into a shared destiny. Triangulum, likely gravitationally bound to Andromeda, may play a role in this merger as well, potentially joining the collision or orbiting the newly formed galaxy that results. Scattered between these giants are the dwarfs, galaxies like Leo I, Leo II, Fornax, and Pegasus, floating above and below the main plane, each one tracing an orbit shaped by the gravity of its larger neighbors. The local group is also more than just a collection of galaxies. It is a laboratory for understanding cosmic evolution. Because it is so close, astronomers can study its members in far greater detail than distant galaxies. This allows them to observe how satellite galaxies are stripped of their stars, how tidal streams form, and how gas is exchanged between galaxies. Above and below the Milky Way, the local group provides constant reminders that galaxies evolve not in isolation, but through interactions with their neighbors. Every dwarf that is torn apart, every stream that arcs across the halo, is evidence of this dynamic environment. Importantly, the local group itself is not static. It is moving as a unit, falling toward larger structures beyond, such as the Virgo Cluster and the Laniakea Supercluster. Within this broader context, the Milky Way, Andromeda, and their companions are merely small participants in a grander cosmic flow, carried along by the gravity of clusters and filaments that extend across hundreds of millions of light-years. But even within this vastness, the local group holds meaning for us. It is our immediate neighborhood, the stage upon which our galaxy's interactions play out. Above and below the Milky Way, then, the local group context reveals a universe that is layered and interconnected. The faint dwarfs orbiting in the halo, the grand spiral of Andromeda looming in the distance, the smaller but significant Triangulum, all of these members form the tapestry of our galactic community. The Milky Way is a titan in its own right, but it is not alone. It is part of a cluster bound together by gravity, destined to merge, evolve, and transform over billions of years. In recognizing this, we come to understand that our galaxy's story is inseparable from that of its companions, that above and below the Milky Way lies not emptiness, but a family of galaxies sharing the same cosmic journey. Beyond the familiar confines of the local group, above and below the Milky Way's disk, lie structures so vast that they make even our galactic neighborhood feel small. This is the realm of the Virgo Supercluster, an enormous congregation of galaxies bound together by gravity, stretching across tens of millions of light years. Here, the scale of cosmic structure leaps to a new order of magnitude. The Milky Way, Andromeda, and their dozens of dwarf companions are but one small node in a far larger network, a single thread woven into the sprawling tapestry of the supercluster. Rising above or plunging below the Milky Way would eventually carry us beyond the edges of the local group and into the domain of this colossal galactic congregation, where thousands of galaxies cluster, stream, and flow under the influence of gravity. The Virgo Supercluster is centered on the Virgo Cluster, a massive collection of over 1,500 galaxies located roughly 50 to 60 million light-years from Earth. While our local group sits on its outskirts, the pull of the Virgo Cluster is profound, shaping the motions of galaxies across a vast region of space. Astronomers estimate that the Virgo Supercluster spans about 110 million light-years in diameter, containing tens of thousands of galaxies of all types, from giant spirals like the Milky Way and Andromeda to massive ellipticals like M87, which dominates the Virgo Cluster's core with its supermassive black hole. When viewed as a whole, the Virgo Supercluster reveals that galaxies, even when grouped into clusters like the local group, are rarely isolated. Instead, they are the building blocks of something larger, webs of galaxies stretching across incomprehensible distances, connected by gravity into massive structures that shape the flow of the universe itself. The supercluster is not a homogeneous blob of galaxies, but an intricate structure made of filaments, walls, and nodes that surround vast cosmic voids. Galaxies are not evenly distributed across space. Rather, they are arranged like beads along threads, with dense intersections where clusters form. Above and below the Milky Way, beyond the halo, corona, and local group, these filaments extend outward, linking our galaxy to others across millions of light-years. The Virgo Supercluster is one such filamentary region, with galaxies streaming along invisible highways of dark matter, flowing toward the gravitational centers where clusters reside. In this sense, the supercluster is not just a collection of galaxies, but an interconnected system of flows, currents, and structures, all sculpted by the invisible hand of gravity. Our local group's place in the Virgo Supercluster underscores just how small we really are. The Milky Way and Andromeda are titanic by our human perspective, containing hundreds of billions of stars each, yet they are only minor members of this greater structure. The true giants of the Virgo Supercluster reside in the Virgo Cluster itself, where enormous elliptical galaxies, some hundreds of thousands of light-years across, dominate the core. These galaxies are surrounded by countless dwarfs, satellite systems, and hot gas that fills the intercluster medium, heated to tens of millions of degrees. The cluster's gravity is so powerful that it shapes the motions of galaxies far beyond its boundaries, drawing groups like ours slowly inward. Above and below the Milky Way, the influence of this distant cluster is already felt, subtly tugging our galaxy as part of a vast gravitational flow. In fact, the Virgo Supercluster is not merely a backdrop to our local group, it is part of our destiny. The local group is falling toward the Virgo Cluster at a speed of several hundred kilometers per second, a journey that will take billions of years to complete. Though we are currently located on the outermost fringes of the supercluster, the gravitational pull ensures that over cosmic time, our galaxy and its neighbors will be drawn ever closer to Virgo's dense heart. This motion is not unique to us. Countless galaxies across the supercluster are engaged in the same gravitational migration, converging on the dense nodes where mass is concentrated. Above and below the Milky Way, when we step back to this scale, the universe is revealed not as random, but as patterned. A grand choreography of galaxies flowing together under the inexorable pull of gravity. What makes the Virgo Supercluster especially fascinating is its role as part of an even larger system, recently redefined by astronomers as Laniakea, a supercluster complex that stretches over 500 million light-years. In this framework, the Virgo Supercluster is not an isolated structure, but one lobe of a far larger gravitational basin. Galaxies within Laniakea, including the Milky Way, are all moving toward a gravitational focal point known as the Great Attractor, located in the direction of the Centaurus cluster. This discovery reframed our understanding of the cosmos. What we once thought of as the limits of the Virgo Supercluster are instead just one region of a vaster interconnected supercluster system. Above and below the Milky Way, therefore, lie not only the structures of the Virgo Supercluster, but the far-reaching currents of Laniakea, shaping the motion of galaxies across 500 million light-years. The Virgo Supercluster also offers a profound perspective on the relationship between structure and emptiness in the universe. While clusters and filaments dominate certain regions, they are interspersed with vast voids where almost nothing exists. From the vantage point of the Milky Way, looking above or below the plane, one might see both. On one side, the brilliant concentration of galaxies in Virgo; on the other, the yawning emptiness of a cosmic void. The interplay between these regions defines the cosmic web, the universe's largest structure. The Virgo Supercluster is thus not just a mass of galaxies, but a node in this web, its boundaries shaped as much by the voids that surround it as by the galaxies it contains. For us, observing the Virgo Supercluster is a humbling reminder of scale. Even the largest telescopes cannot capture it in a single image, for it spans too much of the sky. Instead, it is mapped painstakingly, galaxy by galaxy, redshift by redshift, until the picture emerges of a sprawling, interconnected region of space. To think that above and below the Milky Way lies this vast structure, containing tens of thousands of galaxies, is to appreciate that our own home is but a speck in an immense cosmic city. And beyond this city lies an even larger one, and beyond that, more still, structures upon structures, all bound together in the web of the cosmos. Above and below the Milky Way, beyond the local group, the Virgo Supercluster stretches like a continent in space, a sprawling web of galaxies drawn together by gravity. It is both our environment and our destiny, the region of the universe to which we belong. To look at it is to see not just where we are, but where we are going, into the dense heart of a supercluster, carried along with billions of stars and thousands of galaxies on the great rivers of gravity that shape the cosmos. Zooming even farther beyond the familiar boundaries of the Milky Way, the local group, and even the Virgo Supercluster, we arrive at the largest scale of structure in the universe, the cosmic web. Above and below our galaxy, stretching across unimaginable distances, lies a vast network of filaments and voids, woven from galaxies, clusters, and dark matter into a structure that spans the observable universe. At this scale, individual galaxies like the Milky Way cease to be the focus. Instead, they become mere points of light along enormous cosmic highways. The cosmic web is the grand architecture of the universe, the skeleton upon which everything else hangs. It is not just what lies above and below the Milky Way. It is the framework that contains it, the vast fabric of existence itself. The cosmic web emerged from the earliest moments of the universe, seeded by tiny fluctuations in density that occurred just after the Big Bang. Over billions of years, gravity amplified these fluctuations, pulling matter into filaments and clusters while leaving other regions relatively empty. What resulted is a universe that resembles a three-dimensional spider's web, luminous strands of galaxies and gas stretching between dense nodes, with vast voids occupying the spaces in between. The Milky Way, when seen from this scale, is just one galaxy within a filament of the local sheet, which itself is part of the greater structure of the Laniakea supercluster. Above and below, filaments continue endlessly, connecting us to clusters tens and hundreds of millions of light-years away. At the intersections of the web lie galaxy clusters, where thousands of galaxies gather in dense knots of matter. Between these knots, the filaments stretch like glowing bridges, channels of galaxies bound together by dark matter. The voids, vast empty regions, are equally important. They make up most of the universe's volume, acting as the negative spaces that define the web's shape. From above, the cosmic web appears almost biological, like the neural network of a brain or the branching pattern of a root system. This resemblance is not coincidental, but a natural outcome of the laws of physics shaping matter on every scale. What lies above and below the Milky Way is therefore not random, but ordered, sculpted into a pattern that repeats across the universe. The filaments themselves are not just strings of galaxies, but enormous rivers of gas and dark matter. Observations suggest that most of the ordinary matter in the universe, up to half of it, resides not in galaxies, but in the diffuse plasma of these filaments, glowing faintly at high energies. These cosmic bridges act as conduits, funneling matter into galaxy clusters and sustaining their growth. Galaxies like the Milky Way are born, evolve, and eventually die within this web, but the web itself endures, shifting only slowly over cosmic time. Above and below our galaxy, beyond all visible limits, these filaments connect us to galaxies billions of light years away, linking our home to the farthest reaches of the observable cosmos. To study the cosmic web is to confront both the immensity of the universe and the limits of human perception. It cannot be seen directly with ordinary telescopes. It must be inferred through large-scale galaxy surveys, which map the positions of millions of galaxies to reveal the hidden pattern. Instruments like the Sloan Digital Sky Survey have shown us slices of this web, revealing long walls of galaxies hundreds of millions of light years across. On even larger scales, surveys of the cosmic microwave background, the afterglow of the Big Bang, show the seeds of the web imprinted in the infant universe. Above and below the Milky Way, then, the cosmic web is not an abstract concept, but a tangible structure, revealed through careful observation and mapped across cosmic time. Perhaps most profound is the realization that the cosmic web is not just made of ordinary matter, but is dominated by dark matter and shaped by dark energy. The galaxies and gas we see are merely tracers, glowing points along invisible scaffolding. It is dark matter that forms the filaments, pulling galaxies into its gravitational wells, while dark energy stretches the voids ever larger, accelerating the expansion of the universe. Above and below the Milky Way, the cosmic web is thus both visible and invisible, a lattice of stars and galaxies supported by an unseen framework, expanding into an uncertain future. The cosmic web also reframes our understanding of above and below. On the scale of galaxies, these terms are defined relative to the galactic plane. On the scale of the local group, they describe the orbits of satellites. But on the scale of the cosmic web, above and below lose their meaning entirely. Here, there is no up or down, no privileged orientation. The web stretches in every direction, infinite in complexity, with filaments threading through voids in a vast three-dimensional lattice. To imagine what lies above the Milky Way is to imagine the next filament, the next cluster, the next node in this infinite net. From our tiny vantage point on Earth, we are limited to what we can see, but computer simulations have given us a virtual extragalactic view of the cosmic web. These simulations, using billions of particles of dark matter and gas, reproduce the large-scale structure of the universe with astonishing accuracy. They show filaments weaving into clusters, galaxies flowing along streams, and voids expanding into vast caverns. In these simulations, the Milky Way is a dot, part of a filament that stretches far above and below, connected to others in an endless network. The cosmic web, in this sense, is not only the largest structure in the universe, but also the most universal. It is the backdrop against which all galaxies exist. Above and below our galaxy, then, lies not emptiness, but connection. The cosmic web is the universe's deepest truth, that everything, from stars to clusters, is part of a larger whole. It is the great architecture of existence, the vast and delicate network upon which the Milky Way itself is hung. To peer into the cosmic web is to see the universe not as a random scattering of galaxies, but as a single, interconnected organism, vast beyond comprehension. And within that web, the Milky Way is but one thread among trillions, a small whirl of light in a cosmos woven from gravity, matter, and time. Above and below our galaxy lies not emptiness, but a magnificent hierarchy of cosmic structures layered one upon another, each one revealing a deeper truth about the universe and our place within it. Beginning with the crowded galactic plane, where stars, nebulae, and clusters fill the thin disk, we ascend into the quiet of the halo, where ancient globular clusters and stellar streams trace the remnants of long-forgotten galaxies. Rising farther still, we enter the dark matter halo, an invisible cocoon whose gravity holds everything together, and beyond it, the gaseous corona, an ocean of hot plasma stretching hundreds of thousands of light years. Above these regions lie the faint arcs of stellar streams and the monumental Fermi bubbles, towering balloons of energy that tell of past eruptions from the galaxy's core. Beyond even these features, satellite galaxies and their gas bridges weave connections to the wider local group, tying the Milky Way to Andromeda, Triangulum, and dozens of dwarfs scattered above and below. And when we step back still further, we find our galaxy embedded in the Virgo Supercluster and, finally, within the immeasurable lattice of the cosmic web, a structure so vast it spans the observable universe. Taken together, these layers form a cosmic nesting doll, each shell enveloping the one inside it, each extending farther into the unknown. Above and below the Milky Way, we find not silence, but evidence of growth, interaction, and evolution. Clouds of hydrogen rain down to feed new stars, streams of stars arc as reminders of past collisions. Dwarf galaxies circle like loyal companions, even as they are slowly dismantled by gravity. Great voids open outward, balancing the filaments that stretch through space. And all of it, the visible and the invisible alike, rests on the framework of dark matter, the scaffolding that holds the cosmic web in place. What begins as the question, what lies above and below our galaxy, becomes in truth a journey outward through the grand scales of the cosmos, from the familiar to the unfathomable. This layered hierarchy also reminds us of our own limitations. From within the galactic plane, we see only fragments, a band of stars across the night sky obscured by dust and perspective. We cannot rise above the Milky Way to view its spiral arms directly, nor can we soar into the void to watch the cosmic web unfold in its entirety. Yet, through science and imagination, we reconstruct these layers, piecing them together through observation, theory, and simulation. In doing so, we recognize that our galaxy is not the center of the universe, nor even particularly unusual. It is one thread among trillions, woven into a fabric that spans the cosmos. Above and below, in every direction, the same structures repeat, reminding us that the Milky Way is but a part of a universal design. And yet, within this immensity, there is beauty in our place. To live within the galactic plane is to witness the glowing river of stars across the sky, the direct evidence of our disk. To study globular clusters is to look into the earliest history of our galaxy, to touch relics older than Earth itself. To map stellar streams is to trace the story of cosmic cannibalism, where galaxies grow by absorbing one another. To uncover the dark matter halo is to acknowledge that most of what shapes the universe is invisible, hidden yet essential. To look into the cosmic voids is to confront silence, and to glimpse the cosmic web is to see the interconnectedness of all things. Above and below, each layer adds a chapter to the story of existence, and together they compose the tale of a universe that is both ordered and astonishing. The closing reflection is not just about what lies beyond the Milky Way, but about what that reveals to us. We are part of a galaxy that is dynamic, evolving, and woven into larger structures we can barely comprehend. Above and below our home lies the evidence of its past and the blueprint of its future. Halos and clusters telling of its birth, streams and bridges revealing its growth, voids and webs foreshadowing its destiny. To step back and contemplate this layered cosmos is to realize that we are not isolated beings in a lonely galaxy, but participants in a vast and interconnected universe. The Milky Way, dazzling though it is not the whole story. It is only one thread in the endless cosmic tapestry. Above and below, galaxies weave together into clusters, clusters into superclusters, and superclusters into the web itself. And beyond even that, the fabric stretches farther still, perhaps infinitely. To wonder what lies above and below our galaxy, then, is to ask not just about our immediate surroundings, but about the nature of the universe itself. The answer is profound. Above and below, there is structure, connection, and meaning, a layered hierarchy that binds us to the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.